It is my greatest honor to receive 2024 Warren Hall Medal. So I thank my colleagues for the nomination, and also the committee, UCOWR committee, for your favorable consideration. So I owe to many people, including my advisors, mentors, colleagues, students, and the family. But there's one group I must acknowledge using this opportunity, and those are journal reviewers. So I remember back to my early years, I often received 10-page reviews for a single paper. I read them word by word and do all necessary changes. I always told my students I write paper with my reviewers. So I thank you very much. So that might include some of you here today. So I really applaud a healthy peer review processes because this is really important for the advances of research, for the benefits of everyone for us. All right. So Branko just talked about the new things. I will bring you back to some old things, okay? So first of all, I'd like to talk a little bit about my very lucky interactions with some former Warren Hall Medal awardees. So I put the years they won the medal. Ari Michelson and Robert Young, they taught me how to figure out not only how, but why on water resource management when I worked with them in a project in China back to early 1990. My first teacher in a US university, Yakov Hems, he told me about systems analysis. He said systems analysis is a philosophy. And over years, I had many mentors, collaborators, such as Professor Winning Ye, Peter Laux, Miguel Moreno, and Jerry Steininger, John Braden, my colleague, and also Gina. So I want to show you an interesting picture. So this picture I taught in 1997. This is the first time I attended an ASAE water conference, and I was the only student. I was unbelievably young around that time. So in that picture, actually, all others, they are already faculty members, and three of them, Professor Wei Ye, Miguel Moreno, Jerry Steininger, they are the Warren Hall Medals. So I want to show this to tell you, actually, Warren Hall Medal has been promoting the excellence in water resources research. And as I said, I'm going to talk about older things. I'm going to share with you my 30-year water resources systems using modern experience using both hydrology and economics. And this goes back to China. So UNDP funded a project on North China water resources management. And so the Chinese team, they tried to figure out how could South North Water Transfer Project contribute to water supply in North China. This is the largest water diversion project in the world, right? But the international consultants, they are mainly economists. They said we have to figure out why is this project good for water supply and economy in North China. And eventually we followed a classic paper written by Robert Young, I just mentioned Robert Young, and also Lee Gray, and those are prominent. They were prominent economists. So the idea here is to put a regional input-output models together with some hydrology, and then we could address a regional water resources plan. And then eventually, that ended with China the loss channel input-output model plus some hydrological model, and this is a major output of that UNDP project. But interestingly, the idea was was brought up by economists such as Warren Laws, Ari Michelson, but the work was done by Chinese water resources engineers. Why? Because around that time, there was no water economist in China, not a single one. And I'm half of them through the project. So then, I'm just sharing with you some of my experience with my PhD study. I started to work on this hydroeconomic modeling for the RSA basin, and also we sent the work to the Maple River Basin in Chile with International Water Resources, International Food Policy Research Institute. And again, so when I worked on my thesis, I thought I might be the one of the first researcher to work on this so-called hydroeconomic modeling. And then after some years, someone showed me this paper by Robert Young, a prominent economist, and John Bradhoff. So I think in this room, if you're a hydrologist, you might remember John Bradhoff, right? He was really, he passed away, he was really pioneer in groundwater science. And around that time, two greatest scientists from ecology and hydrology, they worked together and published this paper. So let me talk a little more about one of the papers from my PhD thesis. So we try to simulate a river basin, including some hydrology and economic stuff. And on the hydrology side, we use this top-down approach. Start from the river basin down to irrigation district, farming fields, and even and in this way, we could be able to describe the hydrology by scales. And on the other hand, on the economic and the social impact, we use a bottom-up approach to upgrade the impact and the economic output from a small scale, from the field scale, all the way to regional scale. So by combining this top-down and the bottom-up approach, we should be able to simulate this watershed. But what did I learn after many years? What I really learned on this model is that this is the first time we built a nonlinear optimization model in general algebra modeling system, and it includes more than 10,000 variables. And that attracted my colleague, Professor Ian Aston. He was an operational, very famous operational scientist. About the Maple-based model, the background of this model is that because of the growth of the San Diego, the capital of the city, and that needs more water. But the primary water right was owned by the farmers, and they plant the grapes and make the famous Ximing wine. This is called the Maple Basin. You might be able to find in a supermarket, you might be able to find a wine, a very good wine from Chile, which is called maple. So the World Bank wants to do this through as a pilot watershed study. So we set up a model, and we simulated three scenarios: a general optimization scenario, and then another scenario including water permit, okay, a little bit more realistic. And the third one feels a little more theoretic. We allow water market, water exchange. And here we compare the economic efficiency, the irrigation benefit per unit of water, and irrigation water withdrawal for two individual agriculture sites, and also the basin level performance. And you can see that, right? So if we move from, if we include water permit and water market, then the efficiency will increase, right? Efficiency will increase. The irrigation benefit will also increase, and irrigation water score will decline. So that means using less water, basically by using less water, we could generate more benefits. And we also tested some scenarios with hydrology, if we have more water or less water. And when we have less water, then the water market will be more active. So when my supervisor, when he looked at the results, he was excited. And he spent a couple of hours with me and tried to figure out how could you get this result. He said this should be, probably should be writing in text. And I told him what I did. What I really did is I added some hydrological relationships into your model. Okay. And he said, oh, I don't understand hydrology, but I believe you. So this is, it looks like this kind of good stuff. But what I learned from that case is that the water market is actually a matter of economics, hydrology, and other disciplines. But it typically appears only in economic terminology. Right? All right, so when I worked on those basic models, I realized we are doing some theoretical work because we assume on kind of unrealistic institutions. We assume there is a basic authority and everyone will follow the authority. But this is not true, it's not realistic. And in the real world, we have different users, different sectors. They compete for water use. They have their own decisions. I always use this map, this picture. This shows the country representative of the Danube River International Commission. The title set up a commission to coordinate the basin management, but you can say that everyone hold their own country picture, and that tell us they represent their own country, right? So then we move to agent-based modeling. That's a little bit related to what Branko just talked about. So basically we want to consider about the individual behaviors, and based on that, we try to understand the collective social structures, and we also deal with interactions between human and the environment. So, fortunately, I got some funding to apply agent-based model to understand the irrigation and environmental evolution in the Republic River Basin. And also, we did some study in the Yellow River Basin in China. And in that project, we coupled agent-based model with hydrology. And then we could simulate the spatially varied water values from upstream to downstream. Because that's important, right? That could be used as a basis for water trade and regulations. And recently, we also use this model to simulate the emergence of biofuel, of bioeconomy. And for that, our assumption is that the different stakeholder groups, such as producers, refinery industry, local communities, and government, they should work together in order to promote the biofuel market. So I want to share with you a little bit of experience about agent-based model. Right? So back to about 12 years ago, in the EWRI conference, we always had a debate if we need agent-based model or we should just do classic optimization. One reason from people had concerns, they said, where did you get data to describe behaviors? All right, and today we don't debate. Why? All right, because now we have more data. Right? We really have, from let me use this big data related to Branko's talk. We have data. We have a lot of behavior data from social media, social sensing, and crowdsourcing. And on the other hand, we have AI or machine learning to derive the behavioral rules. And I just found out this is the numbers of papers on agent-based model for river-based management. In 2000, only a few papers around the world, but today is almost 1,000 papers per year. Right? People don't debate. People don't debate. And this is hopefully AI or data will really bring us to make our agent-based model more realistic. Okay, so once I finished my PhD, I looked for a job, and then I was interviewed by a colleague from International Food Policy Research Institute, and sometimes people read that as International Flour Policy Research Institute, because that's more consistent with my background. And the person told me, look, I could simulate the food production in the whole world over years like this. And they have a flagship model sponsored by the World Bank. I said, oh, this figure may not be right. And it should look like this, right? Because even worldwide, because of the variability, climate variability, hydrological variability, water availability, it should look like this. And it might also look like this. If we consider about climate change, we might have some systematic decline of the water availability. And he got excited. He said, "You get the job. You get the job." And this is why I was able to jump up from a basic model to a global model. So by doing this, why should we do this? By doing this, we could find out if we reduce the groundwater pumping in the U.S., in Okinawa aquifer, that might end with more pumping in India and groundwater depletion in India and also in China, because the U.S. plays a critical role in the international food market. If U.S. reduces water use, food production, and that will push other countries to use more water and produce more food for themselves. So I got excited about this. But I also like to share with you some really unintended or unexpected relevance of my global water and food modeling work. One is the global hydrology. In early 1990s, there was only one global hydrologic model, which is called the water gap. When I made my presentation, I sometimes get comments from hydrologists. They said, this is just the first model, right? But think about today, many of us, we are proud to be a global hydrologist. And the other thing is the so-called virtual water flow. You might have heard about that. So that talks about how food trade affects the water uses at the country or local scale. I really don't realize, like, our work was, by some people, was taken as a start of, at least or some relevance to those big things. But unfortunately, I did not continue that. Otherwise, I could be famous. I really could be famous by continuing on this global work. Once I joined the University of Illinois, I realized I'm not that ambitious. I probably should do some more small-scale work. And that made me some way jump down to reservoirs. Okay. Why was that? So basically, reservoir represents a major engineering infrastructure, and also it shows one of the biggest concerns on environmental sustainability. More importantly, as a professor in a university, we want to do some academic work. Right? Reservoirs have been used as the fundamental unit for water resource systems analysis. So I always show this slide to my students. So even a single reservoir is coupled glacier in resistance. Right? It's affected by hydrological variability and long stationarity. It's affected by the market. So that is consistent with the economists, because they always criticize our engineering models. They say, when you design a reservoir, you assume you already know the water requirement. they don't like us to use the demand because demand varies with the market, right? So, and also recently we realized we should use the reservoir to regenerate the environmental flow to the downstream fish. And as Branko just mentioned, we used to use the so-called minimum flow, right? Minimum flow that could satisfy the downstream ecosystem habitat. And the ecologists and the biologists told us that's not cool. We need a flow regime. So the reservoirs will not only be used to generate flow regime for human purpose, but also for ecosystems purpose. So let me just talk a little bit about the reservoir operation policies. So we usually talk about standard operation policy because this is very simple. We use as much as we have for the current demand. And then what about the risk for the future? If we have water shortage in the future, what happens? All right, so that ends with the so-called hedging. The hedging means we have to, even we have a lot of water, we could satisfy the maximum demand for the future. For the present, we might still consider about to reserve some water, to have some carry or storage, to avoid the serious water shortage in the future. So that then for that we have the hedging role. So I have 10 minutes. Okay. All right. So the hedging role actually is based on economics. It says the marginal value of water. If you use 1 more unit of water, the benefits for current and the benefit for the future should be identical. This is the standard economics. And then, but if we consider about the uncertainty in the future, that's always the concern of hydrologists, right? Then this may not be very straightforward, right? So that ended with the so-called stochastic hydrology, and also people do numeric modeling and analytical models to deal with the complexity. So I just want to share a little bit of insights about hedging. So I mentioned SOP, standard operation policy. We use that a lot in the real world. But based on some kind of work, we found out this is the optimal policy when the utility function, when your objective function is linear. But that's not true in the real world, right? And we also found this is affected, the hedging affected not only by water availability, but also by people's, the operators' behavior, stakeholders' behavior in terms of the risk aversion and also the market and the time preference. Okay. So this is a little bit too complex, but I really just want to share with you, maybe I've got everything here. I want to share with you. So based on the classic optimization model, to minimize the loss for the future and loss for the present and loss for the future, we could derive the risk tolerance. We could also derive the marginal risk tolerance, which means if with certain level of hydrology, with 1 unit of hydrologic variability, how that affects the risk tolerance for behaviors. And we found out actually we have 3 types of hedging. So when the current risk tolerance is higher, when people realize they have more water, then we use this convex hedging. We put more priority for the future instead of now. On the other hand, if people have less risk tolerance for present, they realize the water, we have some serious water shortage, then the concave hedging is the choice. The most widely used role is the so-called linear hedging. So that linear hedging is rooted with the principle of the identical marginal risk tolerance for now and the future. All right. So this is only. I'd like to use this slide to promote students to work on reservoir operation because they found this might be a kind of boring, right? The reservoir operation is kind of boring because we only maximize something, minimize something. And this is what we usually do in this numerical simulation or optimization model. So when we move to the first order, that means we use the marginal value. So that is usually used in analytical models. And further on, we will want to represent the risk attitude to our model to fully understand what is the insight of your hedging policy. Then we have to use the second derivation, second higher derivation. So that's basically used in analytical models. So my message here is that reservoir operations usually are a matter of water resources engineering, economics, and other disciplines, but it typically appears only in water resources engineering terminology. Okay? So based on my experience, I try to answer this question: can we do better today? Yes. We studied with four-time code. We could not describe the basic network, let alone the complex hydroeconomic relationship. Once we have GAMS, we can do much better. But today we have, with more powerful computers, with promotion to the interdisciplinary research and education, and also the data, right? More data. I believe we could do. We have better conditions to do better on this interdisciplinary research. So actually, this attempt is not new. Right? Back in the 1950s, we had the so-called Harvard Water Program. The Harvard Water Program, it emphasized interdisciplinary study, especially hydrology and economics, taking advantage of computers, systems, operations research. And the Harvard program actually ended with huge impact in academia and real-world engineering. But after 60 years, people brought up another method, which is called social hydrology, which means basically we still have to do more on the human-water interactions. So it's interesting. Harvard Water Program was brought up by social scientists. And this social hydrology, after 60 years, was brought up by hydrologists. So I'm thinking about, have we already found a way to work together, or what is the next? Are we still waiting for another keyword to bring us together? And let me skip this slide, and I really want to share with you my message based on this thought. Many real-world water problems are actually a matter of both hydrology and economics, but they're only studied in a single discipline, with the other being regarded as either trivial or overcomplicated. This is my personal observation. Okay. Thank you very much. All right, at the end, I pulled some relevant references to this talk. So here you can say I have already used some of these references in my presentation. And so those are some papers or reports from my own group or some other researchers. Next slide. Okay, so this is another page. As you can see that most of the papers are from my own group, which were discussed during the presentation. But there are also work from others, such as the social hydrology from Professor Sivapanan, and also there is a paper from Professor Laux and Van Beeks on water resources and management, a review of water resources management. And finally, as suggested by Professor Stephen Burgess, he's a professor emeritus of civil and environmental engineering at the University of Washington, Seattle. And he suggested me to include these three references. They are all about interdisciplinary work for water resources management. And two of these references are actually about an interview with two people, the very important people. One is Arthur Mass. So he's one of the pioneers of the Harvard Water Program. And the other one is late Professor Gilbert White. Probably many of you know that he's the father of the modern flooding control in the United States. So in both interviews, they talk about the interdisciplinary nature of water resources management. And also Martin Rose, he also wrote about kind of historical milestones on national water policies or politics. And so you can say this one provides some comprehensive comments on the interdisciplinary work of water resources. Thank you.